Alrighty guys, so hopefully you already saw the lecture 14.1 and 14.2. And so this is, now I'm going to go over the homework. So obviously I'm doing that as well as I go over it. So that way if you have any questions you can review with this video. And hopefully after watching this and the other lessons, this chapter will be pretty straightforward and easy. Okay, so let's go ahead and dive right in. So it says here, the graph models a baseball schedule for a week. The vertices represent the teams. Each game is played. Each game played is represented with an edge between two teams. How many games are scheduled for Boston during the week? And list the teams they are playing. How many times are they playing each of these teams? Okay, let's see. The number of games scheduled for Boston. So let's look at this. Boston has, it's hard to see that. Okay, I can zoom in. Good. Boston has each edge of the game, 1. Basically asking for the degree, right? Let me just get this to marker. 1, 2, 3, 4, 5, 6. I see it has a degree of 6. 6 means that's how many games it's playing, right? So, I gotta clear this. Okay, so I'm gonna zoom out. Can't zoom out. Oh, there it is. I'm gonna put 6, and we're gonna see the answer is gonna be 6. Okay, 6 is my degree, or 6 is the number of edges. The next part, list the teams that they're playing. So let's see. Boston is playing Jacksonville. Boom. Boston's playing Milwaukee. Boston is also playing San Diego twice actually. And Boston is playing Atlanta. Boston is not playing Phoenix, as you see that. Okay. So let's go ahead and put check answer. Now how many games? So let's see. It's playing Jacksonville just once because it has one edge connecting it. So it's going to be 1 for Jacksonville. For Phoenix, let's see. For Phoenix, it doesn't have any games, so you're going to put 0. For Milwaukee, it has 1. And for Atlanta and San Diego, it has San Diego's 2 and Atlanta's 2. And it should add up to 6, so that we have a degree of 6. So that's it. Really straightforward. Next question. I'm just going to go and read the question before I read this. It says, do the positions of Montreal and Pittsburgh correspond to their graphic locations on the map? Oh, okay. So this is the question. I remember this one. You can see anything you want, and you can make the graph look however you like. Remember equivalent graphs? So, in other words, in a map, in a U.S. map, is New York here? Oh, it's not drawing. Sorry. Is New York going to be here, and Philadelphia north of New York? No, quite the contrary, right? It should be New York is up here, and Philadelphia is south of it, right? So it's not representing the real graph. But what is important, it's actually a baseball schedule. So what it represents? It's representing a baseball schedule. So is the New York team going to play Philadelphia team? Yes. That's what it means. This is it's not describing the relative locations between New York and Philadelphia. So this is not graphic. Okay? If the position of Montreal and Pittsburgh do not correspond to their graphic locations, is the graph drawn incorrectly? No. Because this is not trying to represent the graph. This is only representing the teams that are playing next to each other. They are playing with each other, right? Suppose, for the sake of argument, that this was supposedly making a graph of, bordering states or cities or whatever. I don't know. Technically, you can draw it completely out of whack and the lines are just correctly connected. Then yes, it would represent it, because we don't pay attention to the actual orientation. We present with the lines, the connections that matter. Anyhow, is it drawn correctly? No, it's drawn correctly. Okay, that's it. So the next one. Vertices A, B, C, and D. Okay. Oh, okay. They're trying to draw this situation. You have 4 points, 4 edges, 4 vertices. Sorry, and you have 1, 2, 3, 4, 5 lines or 5 edges. You have line AB. Okay, I'll start with the loop. DD is a loop, so it has to have a circle like that on D. So, well, I guess only this one has it. So it has to be C, but let's see if it has the rest. Does it have BD and BC? BD, BC, yes. Wait, actually an AB, so there's AB. It's missing AC, although I see a line there, but it's not really darkened. Yeah, it doesn't have AC, but so I'm going to assume it's not meant to demonstrate, to be shown, okay? Alright. It says, explain why the two figures shown. I was went over here. Okay. So this has a connection between A to T. A connects to all three of them. Did A connect to all three of them here? Yes. G connects to A, which we already proved, and to T. Correct. N only is to A. Correct. And T goes to G and A. G and A. Yeah, it's their equivalent. And then why are they equivalent? Because the edges are connected correctly, or at least connected the same way. The vertices are connected the same way. I'm sorry. Vertices are connected in the same way. Yes. The graphs have the same number of edges. Yes. The graphs have a number of edges that match a number of vertices. I don't know what that's supposed to say. I think that's irrelevant. The graphs have a number of edges that matches the number of vertices. That literally makes no sense. D. The graphs have the same number of vertices. Yes. I would say that's the answer. That's even wrong. Oh, no, that's right. That one made no sense. All right, so draw a third equivalent graph. Choose. Okay, so we're gonna try to graph this differently. So I know it's not gonna be C because A only connects to N. We know that, and A is N. So we're gonna look at N. We're gonna focus on N just to make this faster. N has only one connection, one edge. So N has one here, N has one here. So A and B are potential. N has two here and here, so we know it's not C or D. And we also know that, let's see, T connects it twice to A and G. To A and G. I don't see a connection here. It has to be A. This one makes sense. Alright. Alright. So, oh boy. So this is a situation we have to read that. And I'm assuming we have to figure out which graph it makes us the best connection. So let me use the drawing feature. Okay, here we go. So students are in a group. Those are all the students. And okay. So here we go. Stinky. So let me just write this here. Okay. Prior to forming the group, Stinky was friends with everyone but Muriel. So Stinky, assuming it's S, has to have every connection but not a connection with Muriel. So let me see. Stinky's connected to this one, that one, that one, that one, that one, that. Yes. And not connected directly to M, correct? Stinky here, 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 here. So far they both, okay, so let me erase what I just wrote. Clear that. So far the first one is fine. Muriel was friends with Zippy. Okay, so we go to M. To Zippy, which is there. To Annette, Hood, Chet, and Earl. So that one's fine here. Let's see if it works here. To Zippy, Annette, to Chet, and oh, it's missing the connection from M to E, so it can't be 2. It has to be 1. Okay, so we're done. Nope. Turn this off. There we go. Now it works. Okay. It says here, which of these two graphs will express this correctly? Let's see. I could see A is connected to B and C just once, so like A, B, C, that makes sense. They both have that, good. A is connected to both north and south once. A is connected to north and south once, okay, that's right. North, south once, okay, so that's good. B is connected to north and south once as well. So B is connected to north and south. North, south, okay. It says here C is connected to also, okay, they're all connected north, south. So C is connected to north and south. Let's see this one. North and south. Okay, that's good. What am I missing here? Let's see. North is connected just once. Okay. South is connected to once each. Let's see this one. North has 1. Oh, wait. I see a mistake. Here, north and south are directly connected to each other. And that's not happening. I don't see a bridge going from north directly to south. Here, north and south are not directly connected to each other. So the answer is A. Okay. You got to really analyze the graphs to make sure it's correct. At least for me. Yours might be different. Let's see this one. Washington is about bordering, I hope. Borders O. So this one goes with that one and that one. So Washington goes with Oregon and Idaho. And No, it doesn't touch Montana, so this is wrong. So it has to be D. Okay. Let's see. So here's the floor plan. Let's see. A goes to B, C, and D. A goes to B, C, and D. B, C, and D. Okay, so they both have A, right? B goes to A, C. Only A and C. B goes to A and C. It's saying it's D, but B does not go to D. B only goes A and C, so it has to be this one. Alrighty. So this is the picture here, and we're gonna put, okay, so the beauty of A. Let's see, A has 1, 2, 3, 4. You can either remember or memorize that A has, that a loop is worth 2 points, or you can just think of how many exits you have. You have an exit going north, south, west, I guess, south, and then kind of like eastish, right? So 1, 2, 3, 4. So A is 4. B has 1. You can clearly see 1 for B. C has 2. D has 2 as well. E has 2 exits. So degree is 2. F has 1, 2, 3. F has 3 exits. Degree is 3. Okay. Let's see. Which of the following, which vertices are adjacent to A? So which one's directly connected? Which one has an edge connecting A? A is connected to B and to C. Only B and C. It's not connected to anything else. So I'm going to put B, C. Okay? So here's the picture. It says, use vertices to describe the two paths that start at E and end at C. Okay. So select two sequences of vertices below that describe paths at vertex E and up at C. So we're just talking about path. It doesn't have to be an Euler path. So for example, E, F, C is impossible because F is not connected to C. E, D, B, C. Let's see. E, D. I can't connect to B, so it's not B. E, D, C, B, C. Let's see. E, D, C. B, C, not possible. Let's look at D. E, D, F, C. E, D, F, C. Nope, can't be that one. How about E, D, C? E, D, C. Yep, this one works. Can I have more than one answer? Okay, let's check this one. E, F, D, C. E, F, D, C. Yep, this one works too. It starts at E, ends at C, and it doesn't. It actually exists. The edges exist. So those are my answers. All right, let's see. Here's the situation. While edge CD is included in the graph. Which one? CD? Okay, this one. Okay. The graph is... okay, so it's connected because if you take this line away, then this line is hovering away. So if it was removed, it will be disconnected. Okay, that's a simple one. Alright, let's see. Just use vertices to describe two paths that start at I and end at D. So, let's see. It starts at I. So I, G, H, D is impossible, so it's not A. I, H, G, F, let's see. I, H, G, F, so far so good, and then D. This is good. I, G, F, E, let's see. I, G, F, E, and then it says go to D, which is not possible. I, G, F, D. I, G, F, D. Yep, that's good. It says here I, G, F, D, B, D. So it's almost the same thing. B, nope, this is not good because we'll cross the same bridge twice. And then I, H, G, I, D. I, H, G. Nope, this doesn't go to I, so it's only those two. I guess there's only two answers for these questions. Let's see, consider the following thing to the right, explain why it's not a path. Let's find out. A, C, D, let's see. A, C, D, F. It can't go back to D because it's crossing over the same bridge twice. So, it is not a path because vertex D appears more... No, that's not why. It's not a path because DF is used twice. That's why. You can't use it twice. Consider the graph on the right. Explain why that's not a path. Let's see. I, H, G, Okay, there's no connection from G to A. So GA doesn't exist. So G and A are not adjacent. Okay, there we go. Last question. Oh boy, I have to watch a video. Okay, so this is the video. Montana connecting to Wyoming and Idaho only. So let me move this over here. Wait. Huh? That's not that. The heck? Let me watch the video.
Now we're going to vertex for the. So we'll draw an edge going Utah.
Okay, so it's not really helping. So I have to see a map. I'm not. Oh, okay. Here we go. I was gonna say I don't know this. Okay, ND is here. Okay, the ND connects to SD. NE. That's good. Does ND connect with IA? No, so this is wrong. That connection shouldn't exist. So we know B is bad. Let's see. I'm just looking at the differences. According to the difference between A and C, I see that AR is connected to MO, just like that. But according to this, MO is not connected to NE. Let's see. Where's MO? MO is connected, even very slightly, but it is connected. This one doesn't have that, so it's not that. See, what's the okay? So the difference between A and D is that there's a connection between these two, NE and IA. Yep, they are connected, so it's going to be D. All right, that's a really cool question. All right, so now we got that done. That's it. We're done with this chapter 14.1, and hopefully this made sense. I hope you guys understand. I'll see you guys later for 4.2. Take care.